Air travel is one of the most fascinating inventions of mankind. This incredible feat, which has turned global travel into a routine part of life, springs from the ingenious science of aeronautics. Beyond transportation, aeronautics is also a key driver in space exploration, leading us to new discoveries beyond our planet. But how did we get here? The dream of flight has long captivated the human spirit, with early concepts and attempts often drawing inspiration from the natural world. Among the most intriguing of these early endeavors were the ornithopters, mechanical devices ingeniously designed to imitate the flapping of bird wings. These contraptions, though primitive by today's standards, marked the first human attempts to engineer machines capable of mimicking the flight of birds. One of the main pioneers of air travel comes from the Renaissance, Leonardo da Vinci. His sketches and designs, which included the first known concepts for a parachute and various flying machines, were revolutionary. His visionary ideas, notably the helicopter, were far ahead of their time, laying a conceptual foundation for future aeronautical exploration. Fast forward to 1783, where the Montgolfier brothers launched the first true hot air balloon. Their groundbreaking invention opened the skies to humanity, demonstrating the potential of using air less dense than the surrounding atmosphere for flight. This initial success with hot air balloons spurred further innovations. Soon the balloons evolved, transitioning from hot air to hydrogen. This shift allowed for higher altitudes and flights less dependent on external temperature variations, vastly expanding the possibilities of aerial travel. The evolution did not stop there. The basic balloon design gradually morphed into more sophisticated and structured airships, namely blimps and zeppelins. These airships represented a significant leap forward, offering greater control, larger capacities, and the ability to undertake longer and more reliable voyages. This was considered the era of lighter-than-air flight. This refers to a type of aviation where the aircraft remains aloft primarily through buoyancy, similar to how a ship floats on water. In these aircrafts, the lifting force that keeps them in the air is provided by a gas that is less dense than the surrounding air. The principle behind this is Archimedes' principle, which states that the upward buoyant force exerted on a body immersed in a fluid is equal to the weight of the fluid that the body displaces. But what does that even mean? Imagine you have a bathtub full of water. If you take a rubber duck and push it under the water, you can feel the water pushing back, trying to bring the duck up to the surface. That push you feel is what we call buoyant force. Archimedes' principle says that this buoyant force is exactly equal to the weight of the water that the duck pushed out of the way when you submerged it. In other words, if the duck pushes aside a cup of water when you dunk it, the buoyant force pushing it back up is equal to the weight of that cup of water. Transitioning from the era of lighter-than-air flight, the dawn of heavier-than-air aviation marked a monumental shift in the history of human flight. This new phase was characterized by the development of aircrafts that were heavier than the air they displaced, relying on aerodynamic principles to achieve lift. George Cayley, known as the father of aerodynamics, distinguished himself in the early 19th century by separating the concepts of lift and propulsion in aircraft design. His visionary ideas laid the foundation for modern airplane design. Following Cayley's theoretical groundwork, Otto Lilienthal in the late 19th century brought these theories into the realm of practical experimentation. Through his extensive glider experiments, Lilienthal became one of the first to achieve controlled flights. His work in aerodynamics significantly influenced future pioneers, notably the Wright brothers, setting the stage for the next big leap in aviation, who in 1903 achieved a monumental milestone, the first controlled powered heavier-than-air flight. This breakthrough was not just about getting their aircraft, the Wright Flyer, off the ground, it was also about developing a method for steering, known as wing warping. This innovation in control mechanisms marked the true beginning of practical aviation and spurred a rapid evolution in aircraft design and capabilities. But what is the science of aeronautics? How do rockets and planes even work? The two most basic and important principles of aeronautics are lift and drag. There are two methods of generating lift, static and dynamic. An example of static lift is buoyancy, or the principle of hot air balloons. And for dynamic, it is the dynamic wings on airplanes. For a ballistic spaceflight, rocket propulsion generates thrust or lift. But what is lift? In simple terms, lift is the aerodynamic force that allows an aircraft to rise and stay aloft. On an airplane, lift is primarily generated by the wings. They are designed with a special shape called an airfoil. The top surface of the wing is curved, while the bottom is more flat. This design causes air to travel faster over the top of the wing and slower underneath it. This difference in speed creates a difference in air pressure. According to Bernoulli's principle, faster-moving air has lower pressure than slower-moving air, so the pressure on the top of the wing is lower than the pressure on the bottom. This difference in pressure creates a net upward force. How? Imagine air as a bunch of tiny particles moving around. When air moves quickly, these particles are spread out as they race over an area. Since they are more spread out, they hit that area less frequently, which means less force is exerted on that area. Less force over an area equals lower pressure. In contrast, when air moves slowly, the particles are more bunched up. They hit an area more frequently, exerting more force, which translates to higher pressure. The top of an airplane wing is curved while the bottom is flatter. When the wing moves through the air has to travel a longer path over the top of the wing and a shorter path beneath it. This means the air moves faster over the top of the wing to cover more distance in the same amount of time. According to Bernoulli's principle, the faster moving air on top of the wing creates lower pressure. The higher pressure under the wing pushes up more strongly than the lower pressure above the wing pulls down. This upward push is what we call lift. It's this lift force that counteracts gravity and keeps the airplane in the air. Newton's third law of motion also plays a role in explaining lift. It states that for every action, there is an equal and opposite reaction. As the wind pushes air downwards, an action, the air pushes the wing upwards, a reaction, contributing to the lift. Lift is a crucial concept in aviation as it must counteract the force of gravity pulling the aircraft down. However, achieving and maintaining flight involves not only overcoming gravity, but also dealing with another fundamental aerodynamic force, drag. Drag is a force that acts opposite to the direction of an aircraft's motion relative to the air through which it moves. It's a type of friction that air creates as it flows over and around the aircraft's body, wings, and other parts. There are two main types of drag that affect airplanes: parasitic drag and induced drag. Parasitic drag occurs due to the shape of the airplane and the friction between the air and the airplane's surface. It increases with the speed of the aircraft. The faster the airplane goes, the more air it has to push out of the way, and the more resistance it encounters. Induced drag is related to the production of lift. As the wings generate lift, they also create vortices and turbulence at the wingtips, which cause drag. Vortices are spinning columns of air that are created by the difference in air pressure at the wingtips of an airplane. As said before, when an airplane wing generates lift, there's higher pressure beneath the wing and lower pressure above it. But at the wingtips, these two pressure zones meet. Because air naturally moves from high pressure areas to low pressure areas, it swirls around the wingtip, creating a vortex. This swirling air can be quite strong and is most pronounced when the difference between the upper and lower wing surface pressures is greatest, which is typically during takeoff and landing when the aircraft needs more lift. And turbulence is characterized by rapid, random, and unpredictable changes in air pressure and wind direction. Unlike smooth airflow where air molecules move in a steady, uniform direction, in turbulence, the air moves in erratic patterns. Some causes of this include variations in air temperature, jet streams, and weather systems like thunderstorms. But how do planes overcome drag? Aircrafts are designed with streamlined shapes to reduce parasitic drag. This includes having a smooth, contoured surface and shapes that allow air to flow over the aircraft body more smoothly. To minimize induced drag, aircraft wings are designed with specific shapes, sizes, and angles. For instance, winglets at the tips of the wings can help reduce the intensity of the vortices and decrease induced drag. However, overcoming drag isn't just about aerodynamic design. It also involves the crucial role of thrust. Thrust is the forward force generated by the aircraft's engines, whether they're propellers, jet engines, or even rocket engines in the case of spacecraft. It's what propels the aircraft forward. For an airplane to move forward and ascend, the thrust produced by its engines must be greater than the drag opposing it. This balance between thrust and drag is what allows the airplane to accelerate and maintain speed. Once the aircraft reaches cruising speed, the thrust is adjusted to balance out the drag, allowing the plane to maintain a consistent speed. Pilots also play a key role in managing these forces. Through various flying techniques, they can reduce drag and optimize thrust. For example, retracting the landing gear and flaps after takeoff reduces parasitic drag, while adjusting engine power helps manage thrust. Flying at optimal altitudes where the air is less dense can also reduce drag and turbulence, making flight more efficient and comfortable. Understanding that this science has only been around for a small amount of time, compared to chemistry or physics, the story of aeronautics is far from complete. It is a field that continually evolves, driven by our innate desire to explore, connect, and reach beyond the limits of our horizons. The future of aviation promises even more remarkable feats. With emerging technologies in sustainable fuel sources, electric-powered aircrafts, and autonomous flying, we stand on the brink of a new era in air travel. These advancements hold the potential to make flight more efficient, environmentally friendly, and accessible than ever before. Moreover, as we continue to push the boundaries of space exploration, the principles and lessons learned from aeronautics will guide us in conquering new frontiers beyond our planet.